We're taking our first foray into proofs using analytic geometry. So what's nice about analytic geometry is that we have the full power of the coordinate axis, okay? And so we're trying to prove that the slopes of perpendicular lines are opposite reciprocals. So we have this m1 equals minus 1 over m2 relationship between the slopes of two perpendicular lines in analytic geometry. So first, let's just talk about the distance formula. The distance formula, and let me just mention, one of the great things about analytic geometry is that we can choose the origin wherever we'd like. We've picked two arbitrary lines. Sorry, that one isn't a very good line. We've picked two arbitrary lines, and then we're going to create we're going to move the origin to wherever those two lines intersect. Why can we do that? Well, look at section 1 in analytic geometry. We're allowed to create this Cartesian coordinate system, put it anywhere. We can put its origin anywhere. So to prove this, we start with two arbitrary lines, OQ and OP. Right? The OP is green, OQ is blue, and these are just what it means to be the distance, right? To find the distance between O and P. Now you'll notice that I'm putting the square on the left side rather than a square root on the right side, and that's fairly typical because if I take the positive square root, it has to be equal. Let's see. So if the let's see, so we're working with the Pythagorean theorem, right? So if a squared plus b squared, right? If c equals the square root of a squared plus b squared, right? It's also true that c equals, right, the right-hand side without the square root. So I'm just doing this. I'm just showing the distance formula squared so that I don't have to deal with the radical on the right-hand side of that equation. Okay, but now we do just have the distance formula. Why? Well, because the distance between P and the origin is x1 minus 0 squared, that quantity squared. And then the plus y, sorry, this should be y1. Okay, so we have x1 minus 0 quantity squared, which is just x1 squared, and we have y1 minus 0 quantity squared, which is just y1 squared. And the same thing is true for the other point, q, the distance between the origin and q. So that's going to be our a and our b, our a squared and our b squared in the Pythagorean theorem. All right, so now we're just going to, this is the c squared, right? If we had calculated if this is going to be a squared and this is going to be b squared, now we're going to look at the distance here, which is the hypotenuse. That's going to be our c, okay? And just applying the distance formula, we have x1 minus x2 quantity squared. Excuse me, the square of the distance is x1 minus x2 quantity squared plus y1 minus y2 quantity squared. And we're going to expand these two binomials, and you'll see why in just a second. Now we need to use the fact that the slopes are opposite reciprocals. That means that m1 equals the negative reciprocal or the opposite reciprocal of m2. Well, if the slope is change in y over change in x, I can calculate the slope here for m1 as y1 over x1, right? Again, I'm using the fact that I'm starting here, I'm calculating the slope going back to the origin, right? So I know that the vertical value is y1 and the horizontal value is x1, right? And I'm doing the same thing here, except after I take y2 over x2, then I'm taking the reciprocal and then I'm putting the minus sign on it. All right, and then I'm writing it in a helpful way and putting, that's the substitution we're going to do in just a moment. All right, so now I take the distance that we calculated between P and Q, and notice that I have this value here, which I can use the substitution on to get this value, and the sign switches. And then notice that it's opposite the value of this, so they add up to 0, what you might think of as going away. And when I do a little bit of arrangements, the only 4 terms I have left are over here. So by the converse of the Pythagorean theorem, and by the way, I added this as a theorem because we didn't have it. The Pythagorean theorem is an if and only if. In other words, if I have a right triangle, then a squared plus b squared equals c squared under the right circumstances, um, under the right labeling. And then if I have a triangle for which I can relabel it so that a squared plus b squared equals c squared, I know that triangle must be a right triangle. So it's an if and only if. It's actually the converse. We know that we have this relationship a squared plus b squared equals c squared now. That's what we've proven right here. So by the converse of the Pythagorean theorem, I know that I have a right triangle. I know that this triangle OPQ is a right triangle, but the most important thing is I know that I have a right angle here, so I know that the lines are perpendicular, which is what we needed to prove.